Oh, that would have been good because I've never been able to get it in 3 guesses. I just got lucky. All right, so just to reiterate, we did the successive approximations here, solve for the volume in the van der Waals equation. We were able to solve it. Was that less than 5 minutes to solve that? Or about 5 minutes? You say less than 5 minutes or about 5 minutes? About 5 minutes. And then I gave you 15 minutes plus an additional 15. I gave you about 30 minutes, right? And so, is that a pretty useful tool to know? Yeah. I mean, it's a fallback method. I mean, if all else fails, go for it. It's better than nothing. You might get lucky. Well, you might get unlucky too, because I've seen 2 pages worth of work with no answer. And then because they got so frustrated, they gave up. But, you know, persistence pays off. Well, anyway, is that a significant error? That's what we call negligible error. And so was it really worth, you know, because CO2 is kind of medium as far as deviation from ideal behavior goes. Was that really worth doing the van der Waals? Was it really worth 5 minutes versus, 10 seconds? The other calculation is like 10 seconds. What do you think? Just to get that extra 0.1 liter? No. And so you know what? I'm not going to bother with the van der Waals anymore here for our calculation for this. We're just going to treat the gases as being ideal. And there's another reason for that. And the other reason for that is this. When I look at this first correction lowers the pressure. You know what the second correction does? If the volume shrinks, what happens to the pressure? The pressure increases. And so on the one hand, this one lowers the pressure. On the other hand, this one raises the pressure. And so the error isn't as big as anticipated because they're self-canceling to some degree. Now, how much are they self-canceling? Well, they aren't perfectly self-canceling. Here. You could see CO2. CO2 has a pretty significant deviation. Ideal behavior is this black line. If it's ideal, it would stay on the black line. But if you look at CO2, wow, that drops way down here. Actually, this was O2, sorry. CO2 is going to be a more significant deviation. I was going to calculate CO2. It's not worth it now. And so CO2 has O2 has a less significant deviation here. Shoot, I wanted to do this one. As you can see, O2 is less. And we saw it was only 0.1. Well, it turns out that CO2, well, look how many atmospheres this is. Because this is close to 100 atmospheres here. And so when we're at about 1 atmosphere, 1 bar, we're almost at the beginning, which means that the deviation isn't so big. And so you'll see the deviations are much more significant. It happens that they're self-canceling here, here, and here. Where one deviation cancels out the other. And then at very, very high pressures, then the volume's significant. Over here are the intermolecular forces. And so the intermolecular forces on CO2 drop the compressibility factor. Anyway, basically it's going to be a pain to calculate the volume using the real gas law. Therefore, we're going to treat all gases as being ideal. Even ones that we know are going to kind of deviate from ideal, like H2O gas. And if you really wanted to get accurate, you could, but you know, for O2, we saw a very minor, kind of negligible deviation. For CO2, we're going to see a bit more significant deviation, but still not huge, not a huge error. Okay. All right. So I don't want to spend too much time talking because we have to do the measurements. What lab are we doing on Thursday?